Yes, last time some people said that the mic turned off after 20 minutes, so if such a thing happens, raise your hand or whatever else you want to raise. Tell us. If you have seen me sitting right at the front of all these lecturers, you may imagine that I'm an extremely enthusiastic follower of all the lectures. To some extent that may be true, but it's more because Axel has been driving me, like a whip or something. Because of the various cancellations, I expected to give my second lecture on Friday, and now it's already the third lecture on Thursday. So obviously I was unprepared for this, and we gently tried to tell Axel that if people cancel, we should have holiday. And it hasn't worked, of course, but so today I'm going to carry on what was my primary duty in this place, to talk about magnetic helicity. I was not sure that in 1.5 hours how fast I will finish, so I just put lots of things. I will not go into all those things. If I do go into everything, then I have to cook up material, more material for the next lecture. So, what I'm going to start with is illustrating. We already discussed the problem of, we already discussed what is magnetic helicity, and we had this dramatic demonstration, self-learning process by cutting various things and discovering links and loops, which we had in the first day. And so now I'm sure all of you have a feel for what is magnetic helicity. But where does it come and hit you in the context of dynamos is what I'm going to talk about today. And I'll not come and deal with solutions today, and I will leave it to the next talk. But I will begin with helicity in the context of galactic dynamos. I'm sure that all of you who came right in the beginning have read through this whole list. And I found that many people came before me into the lecture hall, so I won't even bother to read through that. So, what we stopped yesterday was to discuss about turbulent dynamos, mean field dynamos in particular, and I just want to put it in the context of galaxies. I'm not going to give Anwar's lectures, and he's going to really dwell at length, and I'm talking about this when he's somewhere outside doing his thing, and before he comes back I will be through with this. What we did was to break up the velocity field into a mean and a fluctuating, and similarly the magnetic field into a mean and a stochastic component. And we discussed yesterday, and Karl-Heinz has been emphasizing this fact in all his lectures, that you try to write down a mean field dynamo equation where this script E, called the turbulent electromotive force, is a U cross B average, and finding that is a closure problem. And in the simplest context, one may imagine that you could write it in terms of something proportional to the mean field and something proportional to the curl of the mean field. Oh, Anwar is back. I thought I'd finish this before you come, but right? And this thing is what we have been calling the alpha effect. Under some approximation, it depends upon helicity in the turbulence. And this is what we have talked about as the turbulent diffusion. In the context of the galaxy, as Anwar will explain in detail, the galactic shear generates the B5 from the BR. You could call these toroidal and poloidal. So it generates the toroidal fields from the poloidal fields, because the centers of the disk galaxies rotate faster than the outer regions because of the flat rotation curve, which Anwar explained. And so you ought to very easily get this component. And you need something to close the loop, as in any of these dynamos, and you need to generate B5 from BR. And that's what the alpha effect does. But of course, I told you that one equation is worth 1,000 pictures. I should tell you the converse. One picture is also worth 1,000 equations. Okay? You may think they are contradictory until you see the numbers, the relative numbers. So it's worth looking at a picture, for example, which was drawn by Anwar, and he will go through it in more detail later, of how helicity is supposed to arise in the galactic kind of interstellar medium. One imagines that supernovae drive turbulence in the galaxy, and you have some parcels of gas in the galaxy stratified. There's less density and pressure as you go up here or as you go down here, and as a parcel of gas rises in this gradient because of in the rotating frame because of the Coriolis force, or in the inertial frame because you are conserving angular momentum, it expands. And so you naturally have, because as it rises it expands, and because it expands as a Coriolis force it twists it. And so you naturally have motions which are helical, where the blob rises and twists relative to the surroundings. And you can estimate that, and that's the kind of cause for the helicity in the interstellar turbulence. And these helical motions are supposed to generate VR from d5. And if you put all this together, and you put some numbers in, which will be done by Anwar, is that you get growth of the mean magnetic field on time scales of 10 to the 8 to 10 to the 9 years, depending upon where you are in the galaxy. There's also a picture from a book by Rusmaikin, Shukurov, and Sokolov. RSS in India is a different connotations altogether. It's a Hindu chauvinistic party. Some of my friends belong to it, but still. So it's called the Rashtriya Sevak Sangh. So Anwar, you have very illustrious collaborators. And these two pictures are, of course, from that book. And I should ask Anwar to tell you the story of how we drew all these pictures, if he has the time. This is the first part of the galactic dynamo, where the shear generates from radial components the phi component of the field. I already showed you this picture. And the helical motions now twist. So suppose you have a bit of helical motion locally, the phi component of the field is pulled up and twisted relative to the surrounding to regenerate radial components to the field. And the idea is that you merge all these little loops and form some colloidal flux. And an important aspect, which is not too often emphasized in the galactic context, is that you have to lose this dashed line of the flux. Otherwise, you don't get the dynamo, because then when you shear back, it's only the bottom part of it which, if you shear, you regenerate the toroidal field in the right sense. And some people have thought that losing this bit of flux, to get the net flux in the disk, could also be a problem. I already talked about one issue, which is mean versus fluctuations, and I already said as much as I know. And I don't know too much more. So I won't say anything more. What I'm going to talk about today is the fact that when you do this, and you see this last picture, that's what I've shown this picture, you have produced these links between the colloidal and the toroidal field. Because you have produced these links, you have produced helicity associated with these links in the mean magnetic field. And we discuss about helicity conservation being a good approximation, at least in many contexts. So you have to ask, if you produce such links, what has happened and what has happened to helicity conservation. And as I said, losing this top part is something which has often been emphasized, in particular by Russell Kulsur. And he's not worried about mean and fluctuations or helicity or any of these things. He's worried only about losing that top bit of the flux. And this is what he often worries about. But I am not going to do that here. Let me just remind you that I already showed this, that magnetic helicity is associated with the links, twists in the field, and it's a gauge invariant quantity provided the field is closed in some volume. And in fact, I'm going to take today, by the end of the day, I may go away from this definition. And I thought I'd show you a different place where helicity is there. And this is a photograph of the Nordita environment in much better times than you see today. Okay? Of course, you may like this environment better than that environment. Okay? Now, so this is from Axel, took this photograph and provided me with this long time back, 1 year, 1.5 years back. And you can see helicity inspires everybody. So this is the symbol which you will see, and your one assignment for the next week or for the remaining part of the week is to find out where this is. And also come back and tell me what is the helicity associated with these two. Maybe Nishant can do this, or have you, one of you, of course, will know already. So what is the helicity associated with this two in our detail? So we already went through these equations, so I won't repeat them. So, if we look at the helicity evolution, it's governed by eta j dot b, whereas the energy dissipation is governed by eta j squared. And what I emphasized in my first talk itself, that this means that the helicity is could be nearly conserved, even in situations where the energy is dissipated on dynamical timescales. And in that case, the question is, where does the mean field helicity arise? And it arises basically because in the picture that why am I saying this? Because one expects the galactic field to have been very weak at some stage in the past, and one is hoping that the dynamo builds it up to the observed levels. So there was no very weak fields to begin with, which means there was weak helicity. Because there is no field, there is no helicity. But there are strong fields today, as Anwar showed from his observations, which means that there are strong mean fields, at least unfluctuating fields, and which means at least that there is large amount of helicity, magnetic helicity. So the thing which has happened is, how does one sign arise? And you would already have guessed that our picture for these loops of the alpha effect, which I showed before, that it was a small line of field which was taken up and twisted to produce for you the poloidal field, is not completely correct, because it ignores the fact that whenever you do this motion, you are actually grabbing a bunch of field lines and driving them to make the poloidal field from the toroidal field. And whenever you take a bunch of field lines and make a right in that, it turns out you automatically produce a twist, an internal twist. Okay? And this is what is illustrated in this diagram, I think, produced by Eric Blackman in the work. And you can see that what he is trying to illustrate is that when you do the alpha effect, you should actually realize that when you are twisting the field line, when you are pulling out the field line and making a loop, you automatically generate an internal twist. So helicity is conserved. The helicity in this context was nearly zero, and whenever you generate some mean field helicity, at least in this picture, you will generate an oppositely signed twist helicity associated with the small scale field. And this is, of course, Anwar already showed this picture, but he forgot to mention his collaborator. Okay? So His collaborator is, of course, Natasha, his wife.
It was a family.
Huh?
It was a family effort.
Yeah, it was a family effort. So, while he was trying to twist the hose pipe, okay, he needed help, of course, to keep one end steady. So you can go and ask him. And so I'm redressing the balance. So you should give proper citations sometimes, otherwise people will. So this picture, or revised picture for the alpha effect, is produced by Anwar and Natasha. And here again you can see that when you have a right here, you automatically introduce a twist. And as Anwar explained, he has colored the hose pipe so that this black is at the bottom here, and this is at the top here, and now it has reversed here. And when you rise it by complete 180 degrees, you have again a twist completely by 180 degrees. So what you can see is the black portion in here and the white portion here. So again, in some sense, the helicity is conserved, and it's in this bright and twist helicity. So what is the big deal about this whole issue there? The big deal is that whereas the rights appear on the large scale mean field, the twists are being generated on the small scale fluctuating field. So the alpha effect in this particular case, and in general the turbulent electromotive force, the component of the turbulent electromotive force parallel to the mean magnetic field, transfers helicity across scales. So it puts one side of the helicity in the large scale and the opposite side helicity in the small scale. Now, even if you have the same sign, same magnitude of the helicity, since helicity is A dot B, and A is curl inverse of B, so you have an extra length scale in A dot B. So the fact that the helicities are equal means the energy, and in particular the forces, need not be equal. The Lorentz force is J cross B. So it turns out that the Lorentz forces associated with the small scale twists are much stronger than the Lorentz forces associated with the right, basically because of the fact that it's on a smaller scale. Okay? So for the same helicity, the small scale stuff will come back and hit you in the dynamo to kind of stop the dynamo occurring, even though you're conserving helicity, much before the large scale field can build up sufficiently. The small scale twist that you have can lead to some back reaction effects. We'll see that more quantitatively a bit later. These are now more real than the hose pipe, because these are simulations by Axel. This is from a paper by Axel Brandenburg, Schlackman, and Sarsen. I was trying to get the other picture which Axel had, but it didn't have the corresponding plots which I want to show them in the next slide. So here some flux tubes have been evolved, and probably more than these pictures, it would be good to show this. That one started with no helicity initially, and then as the tube evolves and rides and twists, and Axel can tell you exactly the setup, you develop helicity both in the small scale and the large scale. So this is the large scale, this is the small scale, conserving the total helicity. So in a buoyant, I think this was buoyant and there was a rotation, right, Axel? Yes. Yeah. So that you develop these riding motions. It also introduced an oppositely signed twist in the simulation. So there is a simulation which shows that whenever you have one sign of helicity which you are producing, in this particular case, the oppositely signed helicity will do larger k or smaller scales, conserving the total helicity. So, from all these points of view, what one sees is that whenever you are trying to make this alpha kind of effect, you are already trying to put some helicity now in the smaller scales. And what does this do? Now I go back to equations because, okay, now I have had too many pictures. So let me go back to some equations. Let's look at this quantitatively and let's look at the helicity conservation equation. Now separately for both the mean magnetic field and for the fluctuating magnetic field. So if you remember, the total, you can do the same thing as what you had for the, when you derived the helicity equation in the earlier thing, what you did was started from d by dt of A dot B. Now you put bars in all these kind of things. So suppose for example, you started with just the Faraday's law of induction for the mean magnetic field, which is d bar by dt. D bar by dt minus curl of E bar. Uncurl this equation so that you get 1 over c dA bar by dt is minus E bar, say minus gradient of some phi bar. So I'm just going to put bars in front of these. And then looked at this quantity. Okay. So you work out what happens to 1 over c d by dt of A bar dot E bar. Using these two equations, you can go through exactly the same algebra, except that you imagine everywhere here there is a bar, which denotes the mean field. Okay? So you will go through exactly the same algebra, and suppose you are in a system where the fields are close and you can forget about these divergences, and soon I will come back to having those divergences. Then the corresponding evolution equation for the mean helicity, mean field helicity, is exactly what I have shown here. D by dt of average of A dot B bar. There are two averages going on here. One is an average to define the mean field, and one is a volume integral over the whole closed volume. Okay? That's my notation here. Is nothing but minus 2 E bar dot B bar. But what is this electric field? This electric field is now the mean electric field. And if you look at the mean electric field, as you saw right from Karl Heinz's lecture, the mean electric field is J bar by sigma, U bar cross B bar by C, but now there's an extra term, which is small u cross small b average by C. So this term, which only led to a dissipation term when you looked at the total helicity evolution, because as I emphasized that you have a u cross b here and you have a b here, and when you take a dot product, that will vanish. Now has an extra term because there is this E bar, sorry, curly E bar, the turbulent electromotive force, whose dot product with B bar will not vanish. And so, the helicity evolution equation for the mean magnetic field becomes d by dt of this volume integral of A bar dot B bar is twice from this term, twice this curly E dot B bar minus the dissipation term. So you now have not just a source term, not just a dissipation term, but also have a source term in the helicity evolution for the mean field. So this is exactly the term, the alpha effect if you want, because if you take the alpha effect producing helicity, this will be alpha B bar squared, but it can even be any mean field. Any turbulent mean electromotive force, if it has a component parallel to the mean magnetic field, will generate helicity in the volume, in the mean field. So that's okay. So that's this equation. It's right, I think. So I'm glad you still have your... it's okay. It came back. Okay. Now, you take this equation and subtract it from the total helicity evolution equation. The total helicity evolution equation, if you remember, was just d by dt of A dot b was minus 2 eta average j dot b. Of course, there may be a 4 pi by c in my notation. And you subtract the top equation from this. What you are left with, if you break A, the vector potential, into the mean plus fluctuations, the magnetic field into the mean plus fluctuations, okay? What you are left with on this side, from A dot B, the cross products, small a dot capital B averages, small a dot capital B bar average would be 0, small b dot capital A bar average would be 0. On the left hand side, you are only left with small a dot B average. Average is integrated over all the volume. On the right hand side, okay, you have this term, the current helicity term, and it will just subtract out j bar dot b bar. From a similar argument, you will just have small j dot b integrated over all the volume. But now again, in the small scale helicity evolution equation, there is an extra term, because on the right hand side of this there was no volume source term. But for the mean field there is a volume source term. So when you subtract it from the total equation, you will just get the same term with a negative sign. So if you stare at these two equations, one for the mean magnetic field and one for the fluctuating field. I think this is dying probably. Yeah, yes. Maybe I should yeah, I can see it in the hand, but I can't see it is.
Yeah. Now you see with the quality of British products, right?
Well done. That's okay.
This big button, right?
This big one. Okay. Wow, I can even do it from here. So Anwar is advertising British products. Of course, you are not a British product.
Well, in the times of recession.
Okay, I agree. So you can see that this equation and this equation, suppose you look at these two, the mean field helicity has a source term which is plus twice the turbulent EMF component along the mean magnetic field. The fluctuating field helicity has the same source term with a minus sign. So if you ignore dissipation, basically this just tells you what we have been saying all the time, that the turbulent electromotive force, the component of it parallel to the mean magnetic field, transfers helicity between these two scales. So while it's generating the mean magnetic field, it's also transferring helicity across scale. But now this equation, if you look at one of these equations, you have the following interesting thing to see. Suppose you are driven to a stationary state of your dynamo, and suppose you are driven to a state where d by dt of this goes to 0, okay, then what it says is that this turbulent EMF, okay, or this 2 should not be there, okay, yes, the 2 should not be there, should just go as minus eta j dot b. Now we already said such terms typically go to 0 in many contexts when the resistivity goes to 0. So it looks as if in a stationary limit there is no component of the turbulent electromotive force parallel to the mean magnetic field in a high magnetic Reynolds number system, or very small component. This has been referred to as the catastrophic quenching of the electromotive force. It's not the full electromotive force, of course, but the component parallel to the field. But it's a component parallel to the mean field which is responsible for closing the cycle. Like the alpha effect is a component of the electromotive force parallel to the mean field. From B phi it produces from the toroidal it produces poloidal field, and in the alpha squared dynamos, from the poloidal fields it will also produce the toroidal field. And that is the thing which is being suppressed for very small eta. Small eta is typically associated with large magnetic Reynolds number. And that's why I have said here it is a catastrophic Rn dependent quenching of this turbulent electromotive force. So, are we in trouble or are we not? That is the question. So, helicity conservation typically predicts that something disastrous will happen to mean field dynamos if you just leave them alone. So this has been seen, this feature has been seen in many different contexts, and I want to go through some of these contexts because we also did not completely understand or believe it before we went through some of these contexts. For example, I showed this very pretty picture of a simulation by Axel where you force turbulence at some 1/5 the scale of the box and the energy went to the full scale of the box. And it's a power spectrum of magnetic field in that simulation which is being shown here. And the magnetic power starts from very weak values and rapidly rises during the initial stages, exponentially grows. So there is no problem with this dynamo. And there's also a little blip which is also rising at some larger scale. But that sine wave which led, where all the power went to the larger scale of the box, takes a much longer time to happen, and it only arises on the time scale where the helicity in the small scale field gets dissipated due to resistive effects. Of course, there need not be catastrophic quenching if this term is important. Okay? And if this term is important, then you could have a situation where this is slowly getting rid of the helicity of the small scale field, and so you may be able to break out of this problem. Here it is not absolutely clear whether there is a small and a large scale helicity. So I want to show you another simulation by Axel, where the forcing is at a much larger wave number, so that you can clearly see the separation between scales that are being produced in the fields here. And in this case, what has been done is to decompose the magnetic field in this box in helical waves. In helical waves with positive and negative helicity in the spectrum. And what is being plotted is separately the positive helicity part and the negative helicity part. And firstly you can see that, and here this is the linear part of the evolution, and in this simulation you get an eigenfunction. Okay? The forcing is at very large wave numbers in this particular case, so resistance is important. So you get an eigenfunction where total helicity is still being conserved, but both signs of helicity are being produced, one at the small scale and the opposite sign at the large scale. Or I was saying the other way around, one sign at the large scale and the opposite sign at the small scale. So there is a rapid growth during a kinematic stage conserving helicity, and that's this part of the simulation. And then everything kind of freezes, and then there is a slow growth and migration of this peak to largest possible scales or smallest possible wave numbers in this box. And that migration is at the cost of dissipating the small scale helicity. In fact, here Axel also has done simulations where when we were discovering some of these effects, where we said, let's just arbitrarily kill the small scale helicity. So every few time steps, you just filter out one sign of helicity at the small scale. Then there is nothing which prevents the growth of the mean field on rapid time scales. So again, in this particular case, until you get rid of the small scale helicity, things do not grow. To each their own thing which convinces them, and the thing which first convinced me was, you have to dirty your own hands. Was the same model which I talked to you about in the previous lecture. The Kazantsev model generalized to include helicity. But when I first did this model, these equations were already known because they were derived by Weinstein and Kicharchinov before. So I thought I must do something new and different so that I have the motivation to rederive this absolutely horrendous, go through this horrendous algebra and rederive this equation. In fact, you can see the derivation in the appendix of our review. And so what I did was to add a toy nonlinear term, which is motivated by something called ambipolar drift in the interstellar medium context. But right now it is just a toy nonlinearity. But this nonlinearity will still preserve helicity conservation. Because as I explained to you, the total helicity volume generation term comes as the electric field dotted with the magnetic field. The electric field itself is a U cross B. So whatever is the source for the velocity field, U cross B dot B will be 0. So whatever I add to the velocity field, whether it's turbulent velocities, ambipolar, nonlinear velocity, whatever it is, it will not change helicity conservation. And this is also a check on the algebra. So what I considered was a velocity field which is the sum of a stochastic U naught and something proportional to just J cross B. So this makes the problem nonlinear. The stochastic component, I still took it as Kazantsev delta correlated in time, so that you can derive differential equations. But now you have a stochastic nonlinear differential equation. Although it's very simple because it's just the induction equation which has been made nonlinear. So you need a closure. So in the induction equation you get a U cross B, so you get a U J cross B. In the equations for the second movement, there will be one more B, so you have to close the fourth order correlators. And the simplest closure that you can do if you have a fourth order correlator is to break it up into products of second order correlators. If you had a third order correlator, then you have a more problem. You have to write an equation for the third order correlator until you get a fourth order correlator. But if you directly get a fourth order correlator, you just have to, one possible closure is to write it as product of second order correlators. So you get the Kazantsev equations for the magnetic correlation function, which was this part. You get an added alpha effect, which I already showed you in the kinematic part. But you get a nonlinear contribution to the alpha effect because of this Lorentz force. And the nonlinear contribution is nothing but the current helicity. And this will turn up in many different contexts again and again. Karl-Heinz already mentioned it in the tau closure. It also turns up exactly in a similar form in this closure. And we get an extra equation for the helical correlations of the magnetic field, which also has this alpha. And in this particular thing, ambipolar drift also introduces what astronomers call ambipolar diffusion. Okay? And so the diffusivity also gets an additional contribution due to the magnetic energy. So because these guys are now sticking in here, these equations for the correlation functions are nonlinear equations. So at this stage, I did all that I could do in this paper, And there were several interesting results I could derive, but I could never really get down to solving these numerically until I caught up with Axel later, and this was our first paper together, and it was done within a few days, which is the time scale on which Axel works, of course. He is not here. He does not work on the resistive time scale. He works on various fairly dynamical time scales. And within, I think I was there for 10 days, within 5 days, this thing was solved. Within another day, it was written. Within another day, it was sent to the journal. We went to a meeting. Within another week, it was accepted. So this is the fastest thing which I have ever done. And I think that's because of my collaborator, not because of me. So you can check explicitly here from this equation that if I look at the helicity, magnetic helicity, it just goes as eta times the current helicity, or if I transform into things which you can see, the system conserves magnetic helicity. So these equations can be solved numerically. So suppose you start with a Gaussian correlator at initial time. Sorry, these pictures are not very nice. Okay. Now this is the magnetic correlation function at some stage. First you get magnetic correlations only on the scale of the forcing. As you wait for longer and longer time, the magnetic correlation function has a peak here, which is due to the scale of the forcing, but it spreads out in the scale. That means the field gets correlated on larger and larger scales as you watch it in time. In the insert is shown what happens to the magnetic helicity correlations. In the beginning it is exactly 0, and it very, very slowly, as the spreading out occurs, the helicity grows. The helicity correlation at the origin is the magnetic helicity average, and it actually keeps increasing. The only way this can happen from the previous equation for h dot 0 can only change on the resistive time scale. So even this system shows that in the beginning you only develop small scales, and only as you watch the system in time, whereas it can only develop these larger and larger scale correlations, as you dissipate helicity. And that takes resistive time, because the only thing which can happen here, so here there is no split into mean, fluctuations, everything. Everything is a random field. The fluctuating field you can think of as on the scale of the forcing. The mean field you can think of not as a mean field, but field at larger scales, random fields which have got a larger wavelength or a smaller k vector. Same thing can also be seen if you look at the spectra. If you Fourier transform those correlation functions, then there's a peak of this energy keeps shifting to smaller and smaller k. And since this is an infinite system, this evolution never stops. As long as you keep dissipating helicity, you keep pushing stuff to larger and larger scales. And the large scale field grows only on the long resistive time scale again. These are also fairly crummy plots which show that as you keep changing the eta, you get slower. As you keep decreasing the eta, you get slower and slower evolution.
So, in this case, what calculates the growing of the magnetic energy, for example?
It doesn't. I mean, the energy is constantly being supplied, and it's just going to larger and larger scale. So if you have the universe, and if you have the universe as the box, and you can keep dissipating helicity, but you keep supplying energy, you will order the field on arbitrarily large scales. There is nothing which will stop it in that sense. Because there is no other Lorentz forces put in here. It's just a model where you have a velocity which you keep forcing, and there is only this ambipolar diffusion nonlinearity. So, what does this mean? So let's take stock. What we have said is that the small scale helicity evolution equation, if you look at its evolution, and if you go to a stationary limit, then it turns out, seems to be that because of helicity conservation, the component of the turbulent electromotive force parallel to the mean field is quenched for high Reynolds number systems. And the only way you can release this quenching is by actually dissipating the small scale helicity. And this dissipation cannot be done by turbulence or by any such thing, because all those things which involved a velocity field dropped out of the equation because u cross b dot b was 0. Whatever was the source of the u. And this dissipation can only be done by the microscopic diffusivity. And so you would end up having a catastrophic Reynolds number dependent quenching of your dynamo, mean field dynamo, unless you can get out of this in some other way. There's some other way which people started realizing was you have to somehow get rid of this nasty stuff that you're generating. When you're running a mean field dynamo and you're generating all this small scale, you are generating large scale helicity by coupling toroidal and colloidal fields, conserving helicity, and you're generating all this small scale helicity. If you can somehow get rid of this small scale helicity, then you would be off the hook and you would still be able to run the dynamo. And so how do you get rid of such small scale helicity? Mathematically, what you would like to do is to change this equation into an equation with some extra term here. Okay? And if I think of helicity, getting rid of helicity, I'm thinking of taking some linkages, knots or twists and taking it out of the system totally. So I need some kind of a flux of this. But it's very difficult to talk about fluxes of linkages, fluxes of twists, because these concepts are global concepts. When we are thinking about helicity, the only way we could make it gauge invariant was to integrate over some closed volume where the fields are all completely not getting out of that place. So what do you mean by flux of helicity? And correspondingly, what do you mean by a density of helicity? But suppose you could sort that problem out, then you would be able to replace this equation, rather than integrating over all the volume in the universe, by some local equation, conservation law, where I say there is a helicity density, its rate of change plus the divergence of a flux of helicity is sourced by radius term and sinc by radius terms. If I can have such an equation, then in the stationary limit I could imagine that the turbulent EMF, the component of the turbulent EMF parallel to the mean magnetic field is not balanced by this term, which is catastrophic for me, but is balanced by this term, which is a flux of helicity. So what all this suggested was that somehow one needs to have helicity fluxes to make large-scale dynamos work. And of course, the screwed experiment which Axel did, what we call the vacuum cleaner experiment, where you just, every few time steps, you just clean out all the small-scale muck, and then let it, again, the dynamo go. Illustrated that if we got rid of all this small-scale stuff, the noise that the mean field theory sweeps under the carpet, you could still make the dynamo work and grow the large-scale field on the dynamical time scale. But you cannot do this. I mean, you have to find a way in which the small-scale field can be naturally got rid of. And that's what I want to talk about next. What are these helicity fluxes? I will actually talk about it tomorrow, but today I want to spend the rest of the time, which I will finish earlier, I think, to just talk about what is helicity density itself, and what do I mean by helicity density and its flux. Yes, Nisha?
this is stationary limit you are considering for only small h?
No, in principle it will be a final stationary limit for everything.
So eta is the same for like a small scale and large scale. So eta going to 0 meaning eta of the term is like absent from the both mean and
Yes, right. But then they just will just change in sign. So the turbulent EMF still has to go to 0 if you look at both those equations. People generally emphasize the small scale equation because the large scale will be also connected to boundaries. And you see, this whole argument has integrated over the whole universe. So until you have such an equation, until you have an equation like this, which is really only possible, as I will say now, for the small scale, you don't, I mean, this is a global statement. In a global sense, helicity is conserved. When you jam, the turbulent electromotive force produces helicity on one side in the mean field, and the opposite side in the small scale field. And when everything goes to some stationary state, the turbulent EMF is already suppressed. And so you are not going to be able to maintain much of a field in that case. Okay? But that's why it is absolutely essential to, although this problem can be stated, to get out of the problem, you need to make a conceptual jump, which was absolutely essential before it could be stated properly. Although people were doing various things about this. So, let me now slightly backtrack and give you a definition for a helicity density. So this is from some work by Axel and myself a few years back. So here we had to backtrack a bit. In fact, in the beginning, we were always trying to use this Berger's gauge invariant helicity, which is all very well, but it cannot define a density for that either. And it was really cumbersome to even try to work with it and see what it all does. So really, the idea came from trying to go back on what actually helicity is. I've been writing helicity as A dot B, and then getting into all these problems about the gauge dependence of this whole definition. But if you go back to the primordial definition of what should be helicity associated with links and twists of the field lines, you go back to what is called the Gauss's formula, linking formula for curves. I think Nishan may have mentioned this in his talk, that if you are given two curves and you are asked whether there is a link between the two curves, then you just need to know the curve parameterized in some way, the other curve parameterized in some way, and calculate an integral due to Gauss. Okay? Which takes the tangent vectors of both these curves, and if this integral is 0, you get no links. If the integral is non-zero, you can measure the amount of linkage you have between the two curves. So when we are thinking about helicity of the magnetic field, it is natural actually to think of it in terms of a linking formula. So this formula is not due to me, but it is good to go back to this formula because this is the more fundamental definition of what is helicity, not A dot B. So you take the magnetic field, and I've just put small b, but it's of course valid for any field B. Take its dot product, so you take pairs of points x and y, take b at x, b at y, and construct this quantity b dot b at y cross the separation vector x minus y by x minus y cube, integrated over all pairs of points, and that is the measure of the linkages of the field with field everywhere else.
Shouldn't that be AX and AY in between?
What is AX?
Wherever in between BX and BY, shouldn't that be AX and AY?
Where is AX? What is AX?
B you are writing in terms of curl, I think. Small.
Oh no, this is all B. That's the beauty of this formula. It has no A in it. Now, physicists looked at this formula and said this is too complicated. Okay? And so, instead of treating everything in terms of B, which is what you should do, you introduce a quantity which is dependent on B, which is the vector potential, by curl of A equal to B. Then you realize from Biot-Savart's law that A itself is given by B divided by this kind of quantity, and this whole thing in Coulomb gauge you can write it as A at x. And then you can go from this definition to A dot B. A is at x, B is at x, B cubed x. But to find the density of helicity, it is good to take this step back and use this fundamental definition of helicity rather than this definition of helicity. They are exactly the same as when you are in the Coulomb gauge, but this is gauge dependent, and this is not gauge dependent. It is just a definition based on the magnetic field itself and the linkage of the field with itself. So it doesn't talk about any gauge at all, because it's only talking about the magnetic field. Whereas if you use A dot B, you are fixed to some gauge, and in particular they are equal if you define the vector potential in the Coulomb gauge, where divergence of A is 0 and curl of A is B. Then you can go from the Biot-Savart's law and write A as B cross x minus y by mod x minus y cubed d cubed y. Plug this in here and get this. This does not help you to define a density because it's an integral over 6-dimensional space with 3 dimensions and 3 dimensions of x and 3 dimensions of y. A density, you want to count something which is the number of something per unit volume, which is just 3 dimensions. So, in general, you cannot define a helicity density. It's not a gauge invariant concept. But if your field is random and the correlation scales of the field, let's say the correlation scale is small l, is much smaller than the scale of the system that you have, then you can split this 6-dimensional integral into an integral over the separation vector and an integral over x plus y. So you make a coordinate transformation. Small r is x minus y and capital R is x plus y by 2. So this is at present just a coordinate transformation, so you just write this d cubed x, d cubed y as d cubed small r and d cubed capital R. Now suppose you now take the average value of this helicity, let's say an ensemble average or something. Then you would pick up the magnetic correlation function here, bx, by average, will pick up some magnetic correlation function. If the correlation scale is much smaller than the system scale, then you can do the d cubed small r integral, keeping the d cubed capital R integral, okay? Because the correlations don't extend over the full scale. They extend only over a small scale. And define that integral over d cubed small r as the helicity density associated with this random field. So I have split up this d cubed x, d cubed y into a d cubed small r, d cubed capital R. The d cubed small r, I have done this integral. This integral, because the correlation function has a finite support over length scale L, okay, if I go to scales much bigger than small l, you will get no contribution. So I might as well take, if I have an intermediate scale, take the integral over an intermediate scale. It still depends on capital R. So physically, what I am doing is to say that suppose we have links all over the place, but the field is only correlated over some scale. Suppose I stand here and the field is correlated only over the first 3 rows, and after that there are no correlations. All the people sitting in the first 3 rows are my friends, and the other people are not. Anwar not included. Ishan is not included. So I count the number of links that I have. So I count, 4 plus 2, 6. Okay? If I go further than that, I have no more correlations. But that is the system. The system is this whole room. Now I go to some other place. I go to the next row. And I look at the number of correlated links that I have. I count that number. Divide by the volume of the correlation space that I have. I form a density of correlated links. This density of correlated links will change with the position I am occupying, this capital R. But it's an absolutely well-defined quantity, provided I have such a scale separation in the system. Provided I have a correlation length which is much smaller than the scale of the system, for this random field, I can define a density of helicity.
No need to call it scale separation. It's just a natural feature of virtually any realistic random field.
Yes.
Finite correlation.
Yeah, finite correlation length, that's right. Yeah, sorry. But then I won't be able to use it in the flux unless I have another scale which is much bigger than this correlation scale. So I do need that way scale separation. So this gives me a notion of density of helicity. Now I have an expression in terms of the field itself. There is no reference now to the vector potential. So I can calculate what is the evolution of this density. And the evolution of this density I can calculate by looking at the evolution of the small scale field, whose equations I know. So then I can derive for myself a conservation law that the density of helicity, and in fact maybe I will not derive this, but at least this is what happens. Turns out that the density of helicity is given, the evolution of the helicity density is given by divergence of some flux, plus exactly these source terms which I had here. And this is now a remarkable looking equation because it allows you to discuss. Now, Nishan, now the mean field is no longer the prime quantity because you cannot do this for the mean field where it's spreading all over the universe. For the fluctuating random field, you can do this. It allows you to discuss how does this helicity density change from place to place, and can I take this correlated links, can I throw the first 3 rows out of the loop and I have a flux of this helicity density. And if I can do that in various ways, then I will get out of this catastrophic wrenching problem that I mentioned. Actually, I didn't want to say much more today. So I will just stop. And he won't tell Axel. He's not here. And I'll just take questions.
Carlo, you say that there are all the same terms, right? But the variables have different dimension. Helicity density has additional length cubed there, right? So how it can be that the terms are the same?
No. This average was actually a dimension. It was integral over dV by total volume. That averages is averages. So they are not.
So anyway, you work with quantities so have the dimensional.
Yeah, even here, yes. Even here, it was A dot B integrated over all the volume, divided by the volume. So it was always the same dimension. It's not different dimension. So this is a slightly important concept for me. So if you have any doubts, clarifications, this is the time to discuss.
Does the inclusion of such a flux means you are transferring the small scale density to real and large scale?
No, this is now spatial transport. This term, on this term, does transport across scales or in wave number space. So it transfers helicity from some scale to some other scale, the turbulent EMF component on the field. This term, this flux which I am talking about, is a divergence in space. So it's something which transports the helicity from one space to another space region. So this is a very strange concept, right? Because helicity you think is topological. So maybe in some sense I'm doing some shearing, squeezing, and all these twists are moving around from somewhere to some other place. Or as I will say tomorrow, the simplest thing is what Anwar suggested at some stage, where you just throw people out. Okay? But this can be derived as one of the terms here, that when you have mean velocity fields out of the system, okay, then it will carry with it the field and it will carry with it the helicity also. That's the simplest of the fluxes. It will be just what I will call the advective flux. Yes, Anwar.
And may I just maybe, it's not a question, formulate what you are saying in different words, just perhaps hoping that maybe it will just help to understand exactly what you are saying.
Yeah.
So with this helicity conservation, the problem is that helicity is the integral, well, usually over the infinite volume, right? And then you say that I want to helicity flux or transport. But then it's a number. You can transport or have a flux of something which has a local density. An integral over the whole space is just a number. It cannot be transported anywhere. So if you want to talk about the transfer of helicity, you must first define somehow the helicity density. For example, consider the energy of a system. The energy system, that many ergs, is just a number. You cannot transfer energy anywhere. It's just a number. You can transfer energy density. So, in order to write differential equations describing evolution, partial differential equations with transport terms describing the evolution of energy, first you must define energy density. This is easy. But helicity, with helicity, it's hard. Because helicity is a global feature. Energy is a local variable. You just integrate rho v squared over elementary volume, divided by this volume, we have energy density of kinetic energy. But helicity, you cannot freely decide over what volume to integrate.
Yeah, so
because of the gauge properties. And this creates enormous problem. You cannot discuss transfer flux of helicity before defining its volume density. And you can only do it for the helicity of a random field because of the finite correlations. If you calculate the helicity of this random field, then because of finite correlations, the removed regions will make no contribution to it because of the lack of correlation and randomness.
So as you can see, Anwar is one of my most ardent admirer of this helicity density definition, right?
So for quite a long time, people were talking about helicity fluxes without defining helicity density. But it's meaningless. How can we talk about the flux of something which doesn't exist? So it was a really important thing that defining helicity density in a mathematically meaningful and physically meaningful way. So it is a conceptual advantage, conceptual step.
Thank you, Anwar. Right.
You're very welcome.
Now we can't go away because Axel has come back. But actually I've stopped, I've finished for today. Because the next step I want to go back to is different. So I'm through.
Okay. So we missed most of that, but then we should thank you. Are there any further questions?
This is all done in a non-relativistic framework, right?
Yes, but that would not be a conceptual difficulty, I think.
Have you looked into any space-time effects that can carry out this?
No. Yeah, I mean, it took me quite a bit of... see, basically this development of defining the helicity density occurred in a program, I think, which Chris was probably in charge, one of the main organizers, because it was a Newton Institute program. And when I gave a seminar right at the beginning, I was attacked by my proctor, I think it was. And I, of course, always can defend myself, that is okay. But then, of course, I was thinking about this more intensely. And in the beginning of this program, I gave a talk where we used the current, Axel and I had developed, instead of using magnetic helicity, the current helicity and its flux, because that's something which is gauge invariant, and we wrote a paper on that, and we were using that to discuss helicity conservation. And the current helicity is a nice thing because it's gauge invariant, but an important aspect which I did not point out here is that if you don't worry about the flux, there are no triple correlations anywhere in this equations. And whenever you have a turbulent system and you're trying to write down some 2-point correlation, it's always coupled to a 3-point correlation. And the current helicity had this 3-point correlation which requires a closure in the volume term, which we never knew what to do with. We just have to hope that it is not going to be important. But magnetic helicity does not have. In fact, in that talk, I said, okay, basically the current helicity is like your wife, but the magnetic helicity is like your mistress. And, you're always fascinated maybe by the mistress, but what do you have to do with the wife? Don't tell my wife. But by the end of this talk, by the end of the Newton program, I was giving a talk at Leeds, the Leeds meeting. We had figured out this definition for the magnetic helicity, and one can actually do much better because the only unknown things can come in this flux. And this is a divergence of a flux, it's a large-scale divergence. So, in fact, this flux itself can have 3-point correlation, which we have not yet figured out what to do with, but there are many useful pieces in the flux which we understand and which we know what to do with. And actually the simplest of them is what Anwar was saying, just throw out things. And this I'll come to next in the next lecture. Yes,
Randall, just from the very fact that you can define density, volume density, for small-scale helicity, and you cannot define it for large-scale helicity, does it mean that only small-scale helicity can be transported by anything, and large-scale helicity can never be transported? So there is this fundamental asymmetry just from the fact that you cannot define what to transport for the large-scale helicity.
Yeah, you see, no, you can transport the helicity, of course, but you can't transport a density again, in the sense that you won't know whether it's here or there or somewhere else. And that's, yeah, there are many things with helicity which we still don't understand completely.
You imagine that you have a region from which there is a flux. For example, let's talk about something simple, for example, just advection. This flow will carry magnetic field, which is heavy. So, and I can now easily say that it will carry with it some magnetic helicity, because I can define its volume density. Yes. But I cannot say that it will carry with it large-scale helicity.
Yeah, because there will be a link which is coming back. See, suppose you imagine that you had some toroidal field and a colloidal field, and there are lots of small-scale twists and helicity in which you are transporting everything out, just physically. You may be pulling the field line, but it may get linked at a large, very far away from where you are pulling it to. And so, in that sense, you will not have transported the large-scale helicity at all.
This means there is an inherent asymmetry between large-scale and small-scale helicities.
There is asymmetry because you are talking about a topological quantity whose density you can only have for this, for these random kind of fields.
But for the large-scale magnetic field, we are already solving the mean field equations. Okay. So you don't really need to worry about modeling anything. You just know all your variables. And if you can, of course, calculate fluxes, or at least the luminosities, surface integrated fluxes, using the gauge, so-called gauge invariant definition of magnetic helicity. But that only works for a volume. But that allows you then to calculate, if you wanted to, but you don't need that for the theory, if you wanted to, you can calculate that luminosity. And of course confirm.
Of course, finally, if you are able to calculate the induction equation to its ultimate limit, then you have no problems at all, of course.
Yeah.
But it is only the fact that we want to try to do mean field models, and then we want to somehow take into account the stuff that we have neglected, which is hitting us every time we are trying to do the mean field model by either direct calculation or by some closure model or any of these things is showing us that just doing the mean field model alone is not the correct thing, because whatever you have neglected is coming and hitting you and suppressing everything. So to try to still work with mean field model, but take into account this thing which is hitting you, we are trying to use this helicity conservation as an additional constraint. So if you were to just work with the total field, then you don't have to do any of this, I guess. But it is the fact that we are always trying to do a mean field theory rather than the total field theory, which is a mess, that we have to do all these things. Is that right?
Yes. So, as Karl-Heinz has been saying in other circumstances, magnetic helicity is not something that comes out from nothing. It is just a property of the equation that we are already solving. So if we are able to solve the mean field equations correctly, it would automatically preserve magnetic helicity. But that's not the case at the moment. So we do know that the alpha effect does produce magnetic helicity at large scales. We also know it does produce magnetic helicity at small scales. But whatever the small-scale magnetic helicity is in the domain, it must act back on the transport coefficients, and it does so only if you have this JB term in it. And that's where the loose ends begin to appear. So Karl-Heinz already explained yesterday, he said quite clearly that in the JB contribution, it would be the background magnetic field rather than the actual magnetic field, whereas Kandu was exactly saying the opposite. And so that's the first very important point of disagreement, and I believe we can hopefully solve that, or have already now solved it. But I believe, and I hope to convince Karl-Heinz and Matthias also, that it is the actual JB really what that enters. However, of course, JB is not really the real thing. It's a tensorial quantity. And once you talk about the corresponding tensorial quantity that you really want to enter, then again you don't really know your evolution equations for that. I mean, you do know the evolution equations, but you don't have a conservation property again in the usual form.
Well, from tensorial form, there is just the product.
I mean, the alpha effect is a tensor. That's really what it is. And the turbulence is anisotropic.
Yeah, so if it's anisotropic, then you get a tensor.
So the thing that enters in the alpha effect is certainly not delta ij times delta b, which would be the isotropic tensor, but it is something.
Wait a minute. The momentum equation contains a vector j cross b. At what point all of a sudden it becomes a tensor?
The alpha effect is always a tensor, and the alpha effect has contributions from, we know already, alpha, let's take the YY component. Now I have to guess here. So normally we write always this, omega dot u, and then we have a delta YY. So what it really would be then is,
omega y.
and maybe Karl-Heinz can correct me here, I think it would be x comma y times uc, and then there would be a corresponding contribution with b, x comma y and bc, something of that form. Yeah. So that would be the YY component, and that's not J dot B, of course.
Okay, yes.
That's really what it is.
Yeah, I mean, I would also say the following thing, that in the simple context, when we are trying to understand using a helicity conservation equation, then we are realizing that there may be ways in which to make the mean field dynamo not catastrophically quench. I mean, the dynamo, the large-scale dynamo, not necessarily mean field. To grow large-scale fields without quenching is possible under certain circumstances, where one is thinking about fluxes and all these things. But finally, at the end of the day, the helicity equation only tells you about the A dot B, not any of these Tensor things. So it is just suggesting to you ways in which to explore to make large-scale field generation possible. It is not going to solve the problem always, because if once you go out of isotropy and these ideal kind of conditions, you cannot just use the helicity equation to fix those, like that other term which Axel has written down. You cannot just fix that by just using the helicity conservation equation possibly. So
you could always say you don't care about mean field theory, you just do the real simulation. But then you may find that the dynamo either works or doesn't work. So what do you do then? Do you say, you want to understand why something doesn't work and why the sun actually works. That's of course the goal of physics. And one of the things that has emerged from this theory is that magnetic helicity fluxes are important to alleviate this catastrophic quenching, which would mean that the dynamo would not work, which you would see then in the real simulation. And so in order to alleviate these fluxes, or this catastrophic quenching, we have to have these fluxes. And one of the fluxes that we do understand are fluxes along the lines of constant shear. I don't think we have talked about this yet, have you? No. So, so one of the predictions then will be, and is, I think Petri will talk about this on Monday, or the following day, is the following. If you have a box where you have contours that work vertically, you expect helicity to go into the vertical direction towards the surface, and if the surface allows you to penetrate the magnetic flux, the magnetic helicity flux, the magnetic helicity will go out. However, if you have horizontal contours of constant shear, the prediction would be that it would go sideways. And so if the domain has a periodic boundary condition, it would come straight back in again. And there would be still no successful dynamo, even though you have shear. And you have an open surface. But that may not help you because the magnetic helicity is not transported towards the surface, because it's transported sideways. So indeed this has been seen so far, and then the next step, which has also been seen, is the following. You just have your horizontal shear, and the prediction would be, what if you make the boundary condition open? Would it work in that case? That's the prediction from the field theory. And then, of course, you do the real simulation and you find that's true. That's indeed the case. So we are trying to argue really that the reason why we do this theory is really because that's the only way to understand things that you would have never otherwise been guessing.
okay.
Yeah, so any other questions? Yes, Anna.
Do you know what's there for lunch?
What?
What's there for lunch? What they have cooked for lunch there? Do you know?
I guess somebody can find out on the internet. Yeah. Okay, so bon appetit to everybody. Thank you.